Okay. Hello everyone. My name is Aditya Anand. I am a PhD scholar at IIT Bombay. I'm going to talk about our work optimistic stack allocation and dynamic heapification for managed runtimes. This work was done in collaboration with IIT Mandi, IBM Canada and IIT Madras. In this work I'm going to talk about the language Java. So the managed runtime for Java allocate objects by default on heap. So if we have a statement like a equals new a, the created object will be on heap. Having objects on heap has several benefits, like from programmer's perspective, it unburdens the programmer from making any complex allocation, deallocation decisions, which further reduces the possibility of having any harmful memory bugs. Also, we have automatic garbage collection, so the programmer need not worry about explicit memory deallocation. But along with that, we have few challenges as well. So if we have object on heap, the access time becomes a bit higher, as we will have indirections while accessing the objects. Also, garbage collection is kind of an overhead for the VM. So to avoid these challenges, one of the popular solution is to use stack allocation. If we allocate objects on stack, we will have less access time, as well as the memory will get freed up as soon as the allocating method returns. So we don't have to worry about memory reallocation. Also, we have the throughput will be high if we allocate object on stack, more likely that the object will be in cache. So these are the advantages for the stack allocation, but we can't stack allocate everything. So to find out the list of objects that we can stack allocate, we perform an analysis called as escape analysis. In case of Java, escape analysis is performed during the JIT compilation time. So the analysis is performed while the program is executing, due to which it's very imprecise. And because of that, very few objects get allocated on stack. We found that across several benchmarks on all popular VMs, very few objects were getting stack allocated. We ran the OpenJ9 VM, we implemented our work on OpenJ9, so roughly 0.16% of the total number of objects were getting stack allocated. So to solve this issue of having imprecise escape analysis and very few objects getting allocated on stack, one could use static analysis for stack allocation. What one can do is they can perform precise context, flow, field sensitive escape analysis statically, and then use the statically generated escape analysis result to optimistically allocate objects on stack at runtime. Note that we are using the word optimistically, because if we are using stack allocations, we have few more challenges. We have dynamic features like dynamic class loading, hot code replacements that allows the code itself to change at runtime. So what will happen that an object that was stack allocated based on the static analysis result might actually start escaping at runtime. So how to safely allocate object on stack in managed runtime is the overall idea of this work. Let's see this with an example. Consider this example. We have a class A, we have a field f of type A, and then we have three methods foo, zar, and bar. In method foo, we have three abstract objects. At line 4, you will see an object O4 pointed to by variable x. Similarly, at line 5, we have object O5. At line 6, we have object O6 pointed to by the field of object O4. At line 7, we have a reference variable p pointing to O6. At line 8, we have a call to method bar. And if you see in method bar, the second parameter is being stored in the first parameter's field. We are passing p and y, which essentially object O6 is pointing to, which becomes O6 pointing to O5 on field f. And at last, we have a call to method zar, and zar is not doing anything. Zar is not changing the points relation in method foo. So statically, we will get this as the points to graph. And if we perform escape analysis on this points to graph, we will say that we can stack allocate object O4, O5, and O6, since none of these objects are getting accessed outside the method foo. Now let's suppose at runtime, a new class, class B, which extends class A, gets dynamically loaded, which is overriding the method zar. At this point, we have used the static analysis result and we have stack allocated O4, O6, and O5. Now, if you notice the overridden method zar, we have a statement q.f equals p. And if you notice q is a parameter which is being passed at line 9 and then is still which is an argument at line 9 and a parameter to method foo. So in this case what is happening is a reference variable q is the object pointed to by the reference variable q is able to access object O6, and hence O6 starts escaping. So this thing is happening at runtime. So if we use static analysis and stack allocate object O6 and O5, we have incorrect stack allocation at runtime. So how do we identify this thing, and what to do in such cases if we are using static analysis is the next thing I am going to talk. So we propose an idea which we call dynamic heapification. So the idea is that if we have a situation like this, if we have stack allocated object O4, O6 and O5, in that case if we find that an object, suppose in this case object O6 was escaping, the first thing which we do is we copy, or we call it heapify, the object O6 from stack to heap, and then recursively heapify all the objects which are reachable from object O6, in this case it's object O5, by maintaining the field relationship as well. And at last we correct all the references from stack to these newly created objects. In this case P will start pointing to this newly created object on heap, and there Y will start pointing to this new object O5. So this is the idea of heapification. But another question which we will think that is, how do we identify the need for heapification? How will we come to know that an object started escaping? For that we have checks, we call them heapification checks, and we generate these checks during the code generation phase of the IL, and we have these checks for all the statements that can change the escape status of objects. So let's see these checks for a store statement. So let's say we have a store statement a.f equals b, where b, the object pointed to by b is the RHS and object pointed to by a is the LHS. In this case what we are trying to find out is that if we have a store statement like a.f equals b, whether b should be heapified or not. So the first check which we do is that whether RHS, the object b or the RHS object is on stack or not. If it is on stack, then we go ahead and we have the second check, that whether the LHS object is on stack or not. If the LHS is on heap, that means that it is accessible from heap and we should do heapification. And if both the objects are on stack, then what we do is we have a address comparison basically. So here note that we are assuming that the stack is growing from stack is growing downwards from a higher address to a lower address. And so what we do in this check is we compare that whether the address of the RHS object is greater than the LHS object or not. If it is greater, that means that that object was allocated earlier than the LHS object, and hence we don't need heapification. That's the simple address check which we put there. So that's the address check we put. If the address is greater, we don't need heapification. If that is not true, then what we do is we try to find out, we try to locate the object, we perform stack work and heapify based on these scenarios which I will explain the next. So there are several scenarios that can happen at each statement. So let's see the scenarios at a store statement. Let's say we have these three methods, method M1, M2 and M3, where M1 is calling M2, M2 is calling M3, and M3 we have a store statement a.f equals b. First case will be, let's say this is the first case where we have a.f equals b in M3, and the object pointed to by b, which is OB, is allocated in M2, and the object pointed to by a, which is OA, is allocated in M1. So our address comparison will check that the address of OB is greater than OA or not. In this case it's false, the condition will fail. We will do stack work, we will find that okay, OB is allocated in M2 and it is being stored in OA, which has higher address or higher lifetime, and hence OB is escaping and we need heapification. This will be the first case. If the case is exactly reverse, our condition check will be true, and OA, since OB has a higher address, condition will be true and we don't need heapification. The third case where actually both objects are on the same stack frame, in this case if our address check fails, we still need to do stack walk. We will walk this stack and then we will find that okay, both the objects are on the same stack frame, we don't need to heapify. If you notice, in most of the cases we are doing this stack walk, walking this stack, so we don't, and which is costly. we don't want to have these stack walks for each heapification checks. So to avoid this stack walking and to make our heapification check efficient, we propose another idea which we call ordering objects on stack or stack ordering. The idea is that a simple address comparison check which we are having should cover the majority of the times. That should cover all the conditions. So let's say we have this case 3, where we had both the objects on the same stack frame. What we do is, along with generating the stack allocatable objects, we statically create a partial order of stack allocatable objects as well. So suppose we have a relation, points relation like this, where OA.F points to OB. We say that OB should be allocated first and then OA. So we are creating an order among the objects as well. Further, we use this statically generated order in the VM to reorder the list of stack allocatable objects. It reduces the cost of heapification check significantly. We observed that. In case of cycle, obviously, a result will not be valid for only for the one source statement, and in that case, we still be doing stack walk. So this is the idea of stack ordering which we use to make our heapification check efficient. Coming to the implementation and evaluation, we implemented our static analysis using the suite framework, and the runtime components we implemented in OpenJ9 VM. We used Decapo suites as the benchmarks, the latest Chopin as well as the N9.212 MRI. We also used the SpecJVM 2008 benchmarks. Our evaluation scheme had two major schemes. The base scheme is the stack allocation with the existing JIT compilers escape analysis, and the opt one is with our optimistic scheme. And then we compute two major things. First, the enhancement in stack allocation with our scheme, and the impact on performance and garbage collection with this stack allocation happening. So let's see the evaluation with stack allocation with respect to stack allocation. So we have two schemes, base and opt. For each scheme, we were measuring three things: the static count. Static count is the number of is the allocation side, basically number of allocation sides. And dynamic count is the actual number of objects at runtime. Stack bytes is the memory allocated on stack during the runtime. So if you observe for the benchmark like GraphG, we improved the static count from 0 to 32, which corresponded to 506 million of objects. Note that these numbers are over a fixed iteration of on a fixed iteration of runs for each benchmark. Similarly, if you observe for H2, we improved the dynamic count from 29 million to 452 million of objects, and significant improvement in stack bytes as well. So we had improvement on several benchmarks. We have much more benchmarks in the paper, and on an average, we had an improvement of 71% in stack allocation and 54% in stack bytes. This means that we are allocating less on heap. Next, on performance. So here we are, so on x-axis we have the benchmark, on y-axis we have the normalized time in seconds. Lesser the time, the better. We have base and opt schemes. So if you observe, we are reducing the time significantly for most of the benchmarks, and results are looking fine for these benchmarks as well. So this is the performance measurement. We also measure the average performance improvement was around 8.8%. We also measured garbage collection. So on x-axis, you can see the max heap size. So x represents the minimum heap size required for running each benchmark. So we have x, 2x, 3x, and the default heap size. And then we are measuring the number of GC cycle happening for each benchmark. We saw good improvement in garbage collections as well. Like the number of GC cycle got reduced. On an average, we saw around 5.3% reduction in GC cycle. Yeah, to conclude, we handled an important O optimization by allocating method local objects on stack frame of their allocating method. We use static scape analysis to optimistically allocate identified object on stack to improve precision without thwarting the efficiency. We ensured functional correctness in case static analysis results do not correspond to the runtime environment. Overall, we are one of the first approach to soundly and efficiently use static analysis results in the JIT compilers. This is our paper. We have described much more things, some more things in the paper with respect to performance as well. Thank you. Any questions?
Okay, we have time for some questions.
Hello, very interesting talk. I wonder whether you have also evaluated a, let's say, radical approach. Just put everything on the stack and don't care. And when you have a method call, you have to kind of save your stack anyway, because when you return, you have to reconstruct the stack to continue the normal control flow in the caller. So I wonder what happens if you just put everything on the stack, save it away when you have a call, restore it when you return.
So we tried putting everything on stack. So in our case, we had, so if we put everything in on stack and things are not correct, we used to see heapification happening since we don't need to keep things on stack. Did I understand your question? Can you repeat?
No, the idea was, I mean, you just mentioned there's a limit on stack space. Yes, that problem anyway.
Yes.
I was talking about something else. Why not just get rid of all the stack walks, of all the thinking, and just put everything on the stack? The only problem that you have is a context switch. But you need handling for a context switch in the normal VM anyway, because after you return, you have to reconstruct the stack so that your caller can continue, right?
Yes.
So if you just extend this functionality and say, okay, then I have a bit more to save because my stack has become huge, wouldn't this be a much simpler approach?
I think we have not thought on this, but I think we can't keep everything on stack. There is a size constraint as well.
But you haven't looked at the size constraint anyway, right, in this
Yes.
one?
There are also objects that escape the current function and go to the parent. We can't keep everything on the stack. Threads also. If there are threads, there also, even if you don't have threads, the objects can go to the parent function, right? So the escaping.
Okay, if you return beyond the current position in the code, beyond the current seed, that is possible. But just going down into nested call trees, it should be possible.
Right. So the notion of escaping objects. The non-escaping objects can be put on the stack. Escaping
Okay.
objects, if you put, that's what you're saying. You have to, for safety, you have to heapify.
Okay, so you were mainly thinking about really the escaping objects, because when you just go down the call tree, then you might be able to just put everything on the stack and save the effort of the escape analysis.
Maybe
Okay,
we can
thank
move
you.
on.
So I know a couple hundred people who have been using stack allocation in OCaml for a couple years, and I think we all agree that by far the biggest pain point is how it interacts with tail call optimization. And so I'm wondering if you ran into any problems with that at all.
So I didn't hear your question. Okay, yeah. So we didn't look into the tail call optimization yet, but I think we have not looked into the tail call optimization actually. Yeah.
It's not common in Java.
Java, yeah.
Does Java even do tail call optimization?
The JVM does, yeah.
Yeah, we have, but it's not so common.
Cool.
So, have you, two things, have you evaluated the performance of your heapify operation first? And second, I assume you're doing this in the absence of JNI and native code that does whatever it wants, right? So, could you like explain?
Yes. So yeah, for your first question, yes, we measured the heapification. So we saw that, like, suppose a program is taking 7 seconds to run a program. We put extra objects which we know that it will get heapified. So we saw that over 1 million heapification caused a 1 second delay. So the heapification cost was not that much. And for your second question, what was your second question?
That was, I assume you're doing this in the absence of JNI, so yeah.
So in case if, so we are not interfering with the JNI, if something is passed to the native methods that are supposed to escape, or we actually did that, like we found that some of the native methods are not doing anything with the object, so we marked them that, okay, if you pass to these native methods, you can still stack allocate because those are not going to change anything.
Okay, so just to make sure I got your thing right, so in case an object is passed to JNI, it's just marked as a heap thing, so you don't touch it.
Yeah.
Thank you.
Okay, let's thank our speaker again.